Okay, so in the last lecture I had talked about a time switch, and I have also drawn a random access memory based time switch structure, and that switch we were doing write operation cyclically and read operation was a cyclic operation. So I was writing in the RAM in order when the slots were coming. So when slots were coming 1, 2, 3, 4, 5, 6, 7 and 8, I was writing them in order actually. And while reading out, I was reading in out of order depending as decided by the control memory. Okay. So that was the structure which I had discussed in the previous class. So now let us actually do another variation of this. This we call as write acyclic and read cyclic. So if I have to implement this, how this will be done? So I call this particular switch as WCRA and I call this one as WARC. So this is what we had done in the earlier lecture. Let us do the WARC configuration. This is almost the same configuration except there will be some minor modifications by which I can implement this scenario. So we will have a speech memory as usual, and there is an input line which is coming, 8 bits parallelly will be coming through 8-bit wide bus, okay. And you will take this same signal and derive a frame clock which is important. I will also derive a word clock, this same thing as we did in the previous configuration. We will use this clock to run a counter, so which will be used as an address, but remember this time we are actually doing read which is cyclically which is happening. So I will be using this counter's output for read operation. Earlier we actually had used it for write operation, okay. So that will be the variation, and I will be having a mux RW bar, the flag, and this of course has to be driven, clock has to go. So clock will also be actually driving this. This word clock will be putting, will be actually triggering the memory. Okay. So this is not an edge driven, this is a level driven thing. Okay, this is not actually required, this is not required here. So this read write flag itself will toggle within a clock period, so this will act itself as a clock. So counter I can actually put one counter value. Now this time the same clock will be used to choose one of the inputs, either the counter or one which is going to come from a control memory. This you can actually observe, this was exactly what we had last time, but only variation which will come is we are actually again assuming that during the one part the clock actually consists of 1 and 0. So during the first half the clock you will be doing a write operation, and second you will be doing a read operation. So this actually means when it will be 0, I will be connecting the counter value for the read operation, it will be reading out at that time, and when it is 1 then I will be doing the write operation which will be decided by this control memory. So the same control memory will now be used for, so when this is 1 that time this control memory should connect here, I can actually do it this way, and the same clock can be used to select this. Okay. And when this clock is 1 I am actually writing, okay, so I have to put a not get here. So in fact if I do not want to put it, I have to just simply swap this, and that will ensure things are happening this way. So, when it is 0 you are writing that time, when it is 1 then you are reading it out. This one is going to come from the controller. This is the address bus, this is the data bus, and of course there will be a read write flag. So, when you are going to do a write operation here, you will be doing a read operation here. So, therefore, this clock, the inverted thing has to be fed here. I think I had forgotten this particular stuff in the previous lecture. So, you can add this correspondingly. So, RW bar for the control memory was not drawn that time. So, this one gives you a complete write acyclic and read cyclic configuration. So, when you are writing is when the word clock is 1. Okay, now this frame clock will be used to do the reset of the counter. So, when it is 1, that time you are reading from here, and for reading you are taking the address for this speech memory from counter. So, this one will get connected here. Okay. And during this period when this is 1, from your control circuitry, from your processor, you can write into the control memory that time. So, all the control signals for this switch block, the control action is governed by this, the map between input to output, and this can be written when the clock is 1 here. When clock goes to 0, this time this counter will be connected to this address bus. So, in which location you have to write that particular slot which is coming here, that will be governed by what is written here in the memory. Okay. So, if when 1 is coming here, so here the one location will tell 5. So, whatever is coming in 5 will be written into the 5th location in the speech memory. So, we will do an example whereby you can actually figure out how the map happens between the two cases. So, let me take a case again. This is same as I am going to have 8 slots in the frame. These are counted as 1, 2, 3, 4, 5 till 8, and I have again these 8 slots, and the mapping has to be done between these two. So, I am actually taking an example whereby I have to decide that at which location what has to be written in the control memory. So, let us do that. So, I am actually taking switching map. So, 1 has to go to 1, basically slot 1, whatever is coming in the input has to be mapped to 3. So, 2 has to be mapped to 5, 3 has to be mapped to 2, 1 has to be mapped to 4 has to go to 1, 5 has to go to 8, 6 has to go to 4, 7 has to go to 6, 8 has to go to 7. In fact, you can take anything. This I have just taken something which is arbitrary map. You can take anything and you can do this exercise for your understanding. So, when I am going to have this is a location in the input, okay, and what is going to be in the control memory? This is a location in control memory, location in control memory, and what is going to be stored in that control memory, the content part. This is a content for write cyclic, read acyclic, and this is a content which has to be kept in write acyclic and read cyclic. Okay. So, there will be 8 locations in the control memory because it is a 8 slot 8 by 8 switch. So, I will have 1, 2, 3, 4, 5, 6, 7 and 8. So, if we have WCRA switch, okay. So, wavelength that write is happening cyclically, but read is acyclic. So, I have to connect from 1 to 3. So, remember when write is cyclic, this one must have been written in the speech memory's first location, and during third slot it should be read out. Third slot it should be read out. So, third location in control memory should contain 1. Okay. So, third slot should contain 1. So, essentially I have to look at this, and based on that whatever is here has to go in the content. Okay. So, because third slot I want to read out from the first location, so third slot I want to read out from the first location. Fifth slot I want to read out from second one, second. In the second slot I would like to read out from the third one. In the first slot I would like to read out from the fourth one. Eighth slot I would like to read out from the fifth. Fourth I would like to read out from sixth. Fourth I would like to read out from 6, and sixth I would like to read out from 7, and seventh I would like to read out from 8. So, if it is a WCRA switch, this is what will be the content in the control memory. Now, let us come back to this configuration. This is the one which we had done earlier. Okay. If I use WARC, which is this configuration, what is going to be written in the control memory? So, I am going to read out from first, second, third locations in the order. I will be in first slot, will be reading out from first. So, if I want to map to third location 1, 2, 3, I should write in the third location. So, in the first slot whatever is coming I should write in the third location. Okay. So, what this actually means, so that when the third slot will be coming here on this side, it will be the third location will be read out in the third stuff. So, 1 will map onto 3, 2 will go to 5, okay, and 3 will go to 2, so you will have 2, 1, 8, 4, 6 and 7. That is what will be the difference. So, you can try out various different maps and try to find out what will be the content in two different kind of time switches. Okay, now let us look at a 3-stage Clos network. I actually discussed about 3-stage Clos network, but I actually had used a crossbars in that case. Okay. So, can I use this time switch to build up a 3-stage Clos network? That is a question we would like to investigate. A Clos network was something like this, where I had some m by n kind of crossbar which have been used. So, I had used multiple of them, say r of them. So, in the middle stage I had used an r by r switch, and correspondingly the third stage will be something like this. I have got a crossbar. Now, question is, can I actually use time switches here? Yes, I think this can be done. I can replace this whole block by a time switch. So, this is an equivalent because I can have a multiplexer and then I create a time multiplexed stream. I can use a time switch here. And then I can have a multiplex stream where the slots have been interchanged through a time slot interchanger, and I can then do time division demultiplexing So, if you look from here, this is nothing but a space switch which we are using here. So, I can technically replace all these first and third stage by these time switch blocks. So, what will happen because of this? So, I will end up in getting a time switch. I am actually putting a time switch here, but there are multiple of them. And I can actually use a demux okay, and I can do similar exercise here on this side. This is a time switch and time multiplex stream. And I have replaced it by time switches. Now, but one important thing which you can actually observe, when you have time slot 1, because this is 8 by 8 slots for example, as an example. So, 8 slots will be here, okay. And once you have 8 slots, you actually can in time slot 1, this is the switch which will be operating. All other switches are meaningless, because in this demultiplexer only this will be corresponding to time slot 1. So, this one corresponds to time slot 1. This will be activated in time slot 2. This will be used in time slot, if it is m by m, so it is time slot m. Okay. So, all of them will be used only in, and each one of them is R by R space switch. Okay. And similarly, when they will be coming, this will be taken in time slot 1, time slot 2, time slot m, and then you get a time multiplex stream coming out here. I can do something, because all these switches are not being used simultaneously. I can remove these, and if I can only use one switch which can in one slot work like this, second slot it can move and operate like this one, and m slot it will operate like this one, I can use only one single space switch, and it will work in time multiplex fashion. Every slot its configuration will change. If I can do that, I do not require these demux and muxes actually, and we get a configuration which is called TST, time space time configuration. Okay. So, this I can actually very well replace this stuff by one single switch which is R by R. Earlier there were many of them, m of them like this, and I just connect these. Okay. So, when time slot 1 is there, here time slot 1, here will be time slot 1, this will be one configuration, input to output map. So, there will be m possible m maps, and they will be now changing every time slot. So, this switch will be changing continuously. So, I have to store it somewhere. Okay. I will store it in a control memory corresponding to this switch. These time switches anyway have control memory, as we have discussed earlier. So, I can actually build, this is known as TMS, time multiplex switch. So, this is actually a single crossbar, but due to time multiplexing it is acting like multiple crossbar switches. Okay. So, if I have a crossbar like this, I am drawing only a small one, the 4 by 4. So, I have 1, 2, 3 and 4, 1, 2, 3 and 4. So, I have to decide in the first time slot which one of these will be active. Remember, these all of them cannot get active, only one of the point in a column can get active, but multiple in the row can get active, actually that is possible. So, these can snap, but all these 4 cannot snap together, only one of them. So, I can do addressable stuff and this can be controlled through a control memory. So, time slot 1 will tell which one of these. So, there will be 2 bits here because there are only 4 possible options which require 2 bits. So, which one of the cross points will get activated, time slot 2 which one of them will get activated and so on. Similarly, I will use these cross points will be addressable, controlled by another control memory, and whatever is a frame clock, I am going to assume these to be synchronized, all the inputs. That word clock and frame clock will actually be used to generate the addresses here. So, the similar structure what we had in a time switch will be required in this case, and this TMS can be put in here, and I get a TST configuration. So, important thing is the amount of hardware reduces drastically here because I do not require large number of crossbars. I can work with much smaller number. So far life was very simple because I had 8 by 8 or m by m I have used, and this configuration I know. Okay. But suppose if I want to build up a strictly non-blocking switch, what I will do? So, in this case, in this crossbar based 3 stage network, what we required was here, if this is m, I need this n has to be greater than 2m minus 1, greater than equal to 2m minus 1. If this condition is satisfied, I get a strictly non-blocking switch. What is the equivalent condition in this time space time switch? Okay. So, this condition will be when the slots here are m slots, I need here at least 2m minus 1 slots. But I have not talked about a time switch which is having different number of inputs here and different number of outputs here. And on the other side, the number of inputs here are larger, it is 2m minus 1 and it is m. So, I need an implementation of a time switch where number of inputs per frame and number of outputs per frame are different. They cannot be implemented by one single speech memory. See, remember in earlier time switch implementations, in first half of the clock I was either doing read or write, and otherwise on the second half of the clock I was doing write or read, okay, the corresponding thing. So, depending on whether it is a write cyclic or read cyclic, I can do it either way around. Okay. So, how to implement this time switch? So, we need to look into this aspect. So, we will look this into this thing in the next module.